Okay, great. So I'll first, oh, I should have before I recorded, please make sure your video is turned off. I do post these videos online, both to Kaltura and also to YouTube as well. And so I value your privacy and do not wish to capture your likeness. So I'm also going to go ahead and turn off my video for the sake of preservation of bandwidth. And so I hope you're all staying warm. The shoveling was unbelievable. My driveway is about 25 feet by 45 feet, and then, walkways and all sorts of stuff. So it's been about maybe 12 hours total of actual shoveling over the last day or so. But nonetheless, today our focus will be informed search. So I'm going to do a slideshow, and it's been a couple years since I've done online teaching with COVID shutdown at my previous institution. So please bear with me for any glitches or rusty edges that I'm trying to go through. So I'm going to minimize the floating meeting controls. I couldn't find my stylus for my sketch pad, so I'm just kind of going to have to fudge it with my mouse if there are any sketches that I will enterprise to do. So while we get started, before we begin the usual administrative bits, the reading has certainly changed, and please make sure you're keeping up with the reading. Project number 2 will be due a week from today. I might change that. I know that there is one of you who reached out to me about some issues related to AutoGrader, so I have to dig into that today. There's some other responsibilities that I have being chair of the department that I also have to attend to. So I'll certainly let you know by either tonight or tomorrow morning on the course Slack channel if that date changes. And certainly you'll see it on Canvas if that date changes. Okay. How's everybody doing on the homework, on the project rather? Good?
Doing.
Okay.
Yeah, good so far.
Okay. All right, so why don't we jump in? But we will start with the question of the day, and those who took my IoT class are used to this, so we'll see how this works out on Zoom. So it's time to hit the road. Well, not now, but at some point, once we thaw, it'll be time to hit the road. And imagine then on your road trip, let's see, imagine then on your road trip, um, you know your destination, right? But you don't know the details of all the roadways and byways and highways that you'll traverse. So, my question for you today is how could you figure out how close your goal destination is if you don't know anything about those roadways? Let's hear your thoughts. I see something in the chat. Okay. Any thoughts about that? As you're driving, how would you figure out how close you are? Yeah, GPS, all right. But let's say you didn't have GPS.
Maybe like you see road signs that tell you the distance to different destinations.
Okay, that's a great idea. So, road signs that tell you the distance. All right, well, I'm going to make it a little bit more difficult. Suppose you didn't have those road signs. What could you do? Could you do anything to try to figure out how close you are to your goal, to your destination? Let's relax this a little bit. Imagine at any moment in time, as you're making your drive, you know exactly the name of your goal. So you know your goal. And let's imagine you know where you are currently. How might you, or what information would you use, or how could you, at a high level, figure out how close you are to your goal?
Are we allowed to ask strangers
About how close you are?
about like how to get to, this destination?
Ah, what if you, that's a good idea. What if you only knew your current location? Hey, where am I? You're in Worcester, Massachusetts, and you know you want to drive to Newport, Oregon.
You would take a road that's in the like direction like east or west the of the destination, like
Okay,
whatever
well,
direction the destination is in.
okay. Okay, thank you, Nikki. Um, yes, you could, knowing that you're going west, decide that if I'm going to pursue a roadway, I'm going to pursue a roadway that's in the westerly direction. Absolutely, because westerly direction will ultimately get you someplace hopefully closer to where you're ultimately intending to go. But this idea of how close you are to your goal, let's say you know Newport, Oregon, and you know the name of that town. You could look up the latitude and longitude, okay? And if you knew you were in Worcester, Massachusetts, all right, well, in addition, you could look up the latitude and longitude of Worcester, Massachusetts. So with that information, how could you figure out how close you are to your goal? Any thoughts on that? Going
I
once?
guess there's like some like quick math you could do, like, sort of subtract, like, I guess where you are from, the total length of the journey, something simple like that.
Okay. And so it sounds like you're getting to distance measure, right? Um, the latitude and longitude give you effectively a kind of coordinate system where you are on the surface of the Earth. And then knowing that, you can figure out a distance. But let me follow up with a question about that. Is the distance the true measure of what your total length of the drive is to your destination?
No, because roads aren't straight.
Roads aren't straight. And so that distance is kind of like a best guess. It's not 100% accurate, but it's good enough as a reference point because as you're driving, if you go further away from your destination, that straight line distance will get larger. If you're closer, that straight line distance will get smaller. Okay. So imagine our road trip, and I'm sort of on this road trip kick, right? And one modality of road trip that I recently learned is to drag or pull rather an RV or camper behind some truck. And so, so much so, this past weekend before it snowed, didn't know how bad it was going to be outside. I went to the RV and camping show that was here in the DCU Center in downtown Worcester. And so, my brother, my daughter, and I looked at a bunch of RVs, right? Sort of learning here about different road trip modalities. And so this is an example RV. And I'm like, oh my God, these things are better than my first apartment, my second apartment, my third apartment, the apartment I had in grad school, and many places where I've lived. And this is literally the inside of one of these, and the walls can kind of move inward to make it more compact. And when you when you reach your destination and you pitch camp, so to speak, you push out the walls and then you push back in the walls when you're moving. This is another view. This fridge is a little bit small, but you have some pretty nice creature comforts in these RVs these days, and you have all sorts of models for all sorts of people, ranging from very luxurious to more Spartan. And they even have these cool little features like this thing in the bottom left. If you're washing out a cup that you use a lot, you rinse it out, you turn it upside down on that, and it drains and dries. They're like, wow, I don't even have one of those. But nonetheless, let's go back to our road trip on Route 20 from Kenmore Square in Boston, near the Red Sox Fenway Park, to Newport, Oregon on the West Coast. And as we said, this is one of the longest routes in the United States. And so if we were to use the Cartesian distance or straight line distance instead of the actual distance, because as Alexander had mentioned, the roadways are not straight, it gives us a good estimate. And that estimate, it's not exact relative to your traversal of the roadways, but it's good enough because it's well behaved. And we'll talk about what I mean by well behaved, about estimating distances between states, and in this analogy, locations on the map to get you to your goal. And so in that case, you're in Kenmore Square. And one of the observations you'll notice is that this distance measure, we'll call it h of n, we'll later call it our heuristic. This distance measure, as you can see, is shorter than the actual distance traversed along the roadways. So we drive some more, and maybe we reach Chicago, and we stop in for a little bit to take a break for a day or two, see the sights. This distance measure, we still measure it, and this distance measure, it looks like it's a little bit closer to the actual distance from Chicago, and we can evaluate this at each location, but it's still shorter. Okay, so we continue to drive along Route 20, and imagine we stop in the Badlands. Now, I want to see this in person someday. I think it's absolutely beautiful, and I hear the sunsets and the sunrises are spectacular in that part of the country in South Dakota. And again, this distance measure, it's faithful. You'll notice that it was longer when it was in Kenmore Square at its longest from our initial or starting state or location. It was shorter commensurately from Chicago, and now it's even shorter when we measure it from the Badlands in South Dakota. And so we continue along in our journey, and maybe we stop into Yellowstone. That's my goal, is to have a Route 20 trip and to see some of the national parks. And again, this distance measure, this estimate, this h of n, is very well behaved. Okay, so this idea of this estimate, this distance measure, is also used in AI, problem solving and search in particular, and it's called our heuristic. And this heuristic encodes some information about your domain, about your state space. Hence, those methods that try to perform problem solving by search that employ heuristics are so-called informed search methods. Previously, what we talked about, where you're uncovering different paths between the source and the destination state in your search tree or your graph, you didn't know any information and were just uncovering paths, hoping to find that you encountered and expanded a node that met the criteria for being a goal state. And so this heuristic, h of n, it's practical, it's experience-based, and it's a kind of a shortcut. It's an estimate. Now, being an estimate, some estimates are very, very good estimates, meaning they're much closer to the ground truth distance, but some estimates can be a little suboptimal, not quite as good. And so one of the things we're going to do is take a look at properties of these estimates, our heuristic, and talk about their ability to give you optimal solutions versus suboptimal solutions and some pathologies and properties along the way. Okay, any questions? And I have the chat window up too, if you're choosing not to answer via audio. No questions? Okay. And so this heuristic, its purpose is to help your algorithm find solutions that aren't necessarily the best, but good enough to solve the problem. And that good enough can help you in some cases because it can also have the effect of reducing time, the number of states that you encounter and expand, as well as space, the amount of storage you need, either on your encountered queue or your FIFO queue. And what you'll find, particularly as your algorithm or as your state space rather gets more and more complex, it gets larger. And even though for many algorithms, it's a polynomial time in your for searching or for time, and maybe polynomial space, compute storage is still finite. And so any opportunities you have to reduce that burden on time and space is of very much is of value. Okay. And so what this can do is effectively reduce your search, and it can make it less complex in terms of algorithmic complexity. It can make it faster. But because this estimate of distance to the goal is suboptimal, it's not the actual distance, you're effectively making an engineering trade-off. You're trading off optimality for the solution path that you find through state space for speed and or time/memory efficiency. Does that make sense? Any questions? And if I had my video on, you'd see me looking back and forth to the chat to see if anyone's typing anything. Okay. So H of n is an estimated cost, and it's parameterized by n, which is your node, and a node is coerced from a state in the state space. And one of the things you'll see in the exposition in the textbook is that they'll make a distinction between state and node, because state refers to a particular instantiation of your environment, your state space, whereas node represents the reduction of that to a search problem. But sometimes I'll use state and node interchangeably, but please know that they do make that distinction in the book. So ultimately, what H of n does, it returns back a value, and that value reflects the solution path, the cost of going from node n to your goal. And therefore, when you give H of n your goal state, it doesn't have to, but in most cases, it's going to return a 0. Any questions? No? I see a direct message that's empty. All right, so I'm gonna go for it. So a motivating example, thank you, is greedy best first search. And it's greedy, again, because you're going to minimize an objective measure. And in this case, our objective measure, f of n, is going to be our estimate, our heuristic, h of n. Now, I couldn't find a good picture that looks like greedy. The dog is just hungry, not greedy, but all right, bear with me. And so the idea then is you're going to pursue nodes in your search problem that have the best or the minimum h of n, our estimate for distance to the goal. And so the big idea here is that in pursuing low values of your estimate, that you're going to get to a solution quickly versus exhaustively in the uninformed search case versus exhaustively exploring all of the paths you have afforded by the successors of each node in your search. So let's take a look at this optimal path finding or solution finding. And we'll refer back, and this is from the book, refer back to the Romania vacation. And so one of the first questions, and I'll pose this question to you, second question, what is an easy h of n for this search problem? What is something that might pop into your mind as I'm going to use this approach as my estimate for distance? Let's hear your thoughts. So okay, I guess we were a little sleepy. And so like we said with the road trip example, going from Kenmore Square to Newport, Oregon, we can use the Cartesian distance, or as they call it in the book, the straight line distance. So let's go with that example. And so we'll note it as they do in the book, HSLD for straight line distance. And in this case, our nodes are the states corresponding to each one of these towns. Now, of course, they've gone ahead and computed these straight line distances, which are different from the distances afforded to you as you traverse the roadways marked that have the individual path costs or the mileage between adjacent cities in the search tree. And so the goal state is Bucharest, which is marked on the map. It's here. And we're going to start out in Arad. And to have a so-called informed search, you need some information about your domain. And that's the case for any heuristic. You need some aspect of your environment, your state space, in order to compute this H of n. Now, in the case of a navigation example, you can get the latitude and longitude of each city by name, and it will typically be the center of that city. And from that latitude and longitude and the equation you can look up online, you can compute the mileage straight line distance. Now, of course, it's not really straight line, right? Because you're traveling along the curved surface of the Earth. But nonetheless, humor me, we can just imagine it's a Cartesian distance. But those are still known, and you can compute that from the latitude and longitude. Now, certainly, being armed with the latitude and longitude is domain information. Likewise, in the Pac-Man domain, you're going to have to know something about the state space. You're going to obtain this from game state, ultimately indirectly through the accessor methods from the game state data object. And so when you compute this heuristic, this estimate on distance for any node, which is the parameter to the goal, this is not computed from the transition model. It's not computed from the actions, and it's not computed from the path costs that you arrive upon. You have to know something about the detail of your state space, typically, when you compute your estimate. Does that make sense? Any questions? No questions? All right. So, of course, and I'll pose this to you to get the cognitive juices flowing, so to speak, this morning. What data structures are we going to use for this greedy best first search? What are your thoughts? Let's hear you share your thoughts on this. Priority queue, absolutely. And we use a priority queue because our objective is when we do our exploration, we're going to expand nodes on the frontier, get a number of successors for each node, and we send them to this data structure. We want to pick off for our next state that we pursue, our next node, we want to choose that one that has the minimum objective value, the minimum estimate H of n. Absolutely. Okay. So we're going to use a priority queue. And in doing so, as we expand the frontier, it's going to, you could call it probe or pursue those nodes that have the minimum value for this H of n. Now, of course, depending on the criteria you use in designing your H of n, that's going to impact the exploration behavior, but nonetheless, it's still going to select the minimum H of n value to pursue each time on each try as the search is proceeding. And so on the right-hand side, the upper right, is a figure that has these H of n values. And as you can see, each city has one. And if we look at Bucharest, which is the second row in that left-hand column, its estimate, H of n, is 0. Okay. And so we start out in our initial state, and our initial state is given. It's Arad, and its H of n value, its estimate, distance to the goal, straight line distance, is 366. So we seed our priority queue with a singular value, which is the start state. That would be unfortunate if we added something else because the problem would not be correct. The solution would not be correct. So we expand Arad, and we produce Sibiu or encounter Sibiu, Timisoara, and Zerend, each of which these nodes are decorated with the h of n objective value. So we have Sibiu, its h of n, its estimate is 253. Timisoara is 329, and Zerend is 374. So these encountered nodes are added to the priority queue, and because Sibiu has the minimum h of n value estimate of all the nodes on the queue, when we pop off of that, it's going to be selected, and we expand this node. So we expand Sibiu, and as we can see, the neighboring nodes, the successors for Sibiu, are Phagaras, Oradea, Rimniku, Vileka, and Arad. And the thing to pay attention to here is you'll notice that Arad reappears on this search tree. Now, of course, yes, Arad is a neighbor of Sibiu, a successor, but you'll notice this thing we're going to highlight, that Arad's distance measure is 366. It's one of the largest among all of the nodes, these encountered nodes, which ultimately are sitting in the priority queue. So yes, Arad is re-encountered in our search, but the search is not going to pursue Arad anywhere near being first because there are other nodes whose estimate h of n are much smaller, and therefore they're going to be pursued first as we explore the search queue. Moreover, Phagaras has right now the smallest h of n value, but as we expand Phagaras, because it is the smallest h of n value on the priority queue, certainly its successors conceivably are going to be even closer in their estimate to the goal. So while, yes, there are other nodes that are on the priority queue, we're going to focus this search in a particular subtree, that subtree that's rooted in a node that has the smallest h of n value. So in effect, we're ignoring parts of this search tree and ignoring this repetition of Arad that appears because it was added or encountered when we expanded Sibiu. Does that make sense? Any questions? No. All right. So we expand Phagaras, and when we do that, of course, we add its successors, namely Sibiu. So Sibiu reappears, and Bucharest. And now the thing to pay attention to here, you'll notice that Bucharest's estimate value is 0. So in spite of all the nodes, some of them are repetitions, that are now on the priority queue, we've encountered them, the preference is to select Bucharest on the next round. We recognize that it's the goal state, and we return our solution. Okay. Any questions? No? All right. So this is a complete solution, meaning that should a solution exist, it's going to return that optimal solution. And this is the case for finite search spaces, not for the infinite search spaces. When we look at the complexity for time and for space, it's big O and the size of the number of vertices or nodes in your problem. And if you have a particularly good heuristic, and we'll talk more in the subsequent slides about what constitutes a good heuristic, we can get big O of BM, which looks a lot like depth first search. Okay. Any questions? And if we look at it, you'll notice we're pursuing nodes that are down the tree, not fanning out across the tree at every depth that we encounter, because we're preferring those nodes that have the smallest estimate h of n. Okay. So let's take a look at A-star search. So for A-star search, we have our evaluative measure, and our evaluative measure f of n consists of two components, g of n and our estimate from a node to the destination h of n. And I'll unpack a little bit what that means. So we have our search space, our search tree that we can derive from our state space, and we begin in our start state. From our start space state, we already know what our goal is. And that goal in a navigation example is your destination location. But in something like Pac-Man, it represents that configuration of the environment reached where all of the food has been consumed. So we expand the frontier, beginning in our start state. And as we expand the frontier, we encounter some nodes. And one of those nodes we encounter is an arbitrary node we'll call node n. And this arbitrary node n, along the way, as we play the transition model forward from the first try to the second try to the third try, so forth, we're going to accumulate those those step costs into a path cost. And if we accumulate that, we're going to call that value of the path cost from our start state to an arbitrary node that we encounter. We're going to call that g of n. And so g of n can be computed incrementally by adding the individual step costs as we explore the frontier, encountering more and more nodes along the way in our search tree. And so this g of n is computed from action costs. So we have that from the environment definition, the environment dynamics. So then from this arbitrary node, we continue expanding the frontier, and ultimately we will reach or uncover some goal that we're going to call node G. But at the point when we encounter node N, we don't yet know what that solution is that we're going to encounter. We use our estimate h of n. And what that h of n does, as we said, it gives us an estimate, a loose approximation, if you will, of the path cost to get to g of n from that arbitrary node that we've encountered that we're calling n. Does that make sense? Any questions? No? Okay. So let me turn back on the camera because I like, let me see. There we go. All right. So then our evaluative measure is going to consist of two things. It's going to consist of the path cost to get from our initial state to that arbitrary node we've encountered, n, plus that estimate from n to the goal. And so when we do a best first search that employs this type of evaluative measure, f of n, that consists of g of n plus h of n, we call that A* search. And this h of n, as we'll see, can be of a number of different sorts. And depending on how you design your h of n and certain properties, it impacts the quality of your search. Okay. Any questions? And so A*, no questions? No? So A* search is just best first search. We're going to use a priority queue, and we're going to use an evaluation function. But with A* search, it's just like greedy best first search, only we're going to include the incremental path cost g of n plus our estimate h of n. Okay. Oops. Let me see. So weird. I haven't online taught in several years. It's kind of rusty, like riding a bike or something like that. All right. So let's see. Let's illustrate this A* search again using our Romania vacation. And so in this case, we're going to compute our h of n, again, as our Cartesian or straight line distance, which is depicted for each one of the nodes in this search problem in the upper right. And we're also going to add to that our path cost that's computed incrementally from each one of the edge weights between nodes in the graph on the left-hand side, the upper left, which are the distances in mileage between neighboring nodes in the tree. So we start out with Arad, and in Arad, our g of n, our path cost, is 0 because we're at the start state. Our h of n is going to be 366. So we add the two together, we get 366, and certainly you populate your priority queue in the beginning at time t0 on our 0th try with that singular node, our start state. So we pick this off the priority queue, and we expand its successors. And again, we get three successors, Sibiu, Timisoara, and Zerent. So Sibiu will notice its h of n value. Sibiu is 253. Its incremental transition cost is 140. We add the three together, we get 392. Timisoara, its g of n is 118. So that is its step cost to get to Timisoara from Arad, plus 329 for 447. And Zerent, g of n is 75, h of n is 374 for a total of 449. So these three nodes we encounter, we place them on the priority queue. Arad has been popped off the priority queue. And because Sibiu has the lowest g of n plus h of n, we're going to pick that off of the queue on the next round. So we expand Sibiu, and its children, or its direct successors, are Arad, Phagaris, and Oradea, and Rimniku Vileka. We see that Rimniku Vileka has the lowest evaluative measure, 413. Its g of n is 220. Its h of n is 193. So we pursue Rimniku Vileka, expand its successors. We get Craiova, Pitesi, and Sibiu at an evaluative measure of 526, 417, and 553, respectively. And so now, if we look at our priority queue, we have quite a few nodes there, but Phagaris that we added when we expanded Sibiu now has the lowest evaluative measure with the g of n plus h of n is equal to 415. So in spite of Arad appearing a second time, of Sibiu appearing a second time, this A-star search pursues Phagaris because it minimizes this f of n equals g of n plus h of n. Any questions? No questions? Okay, so I keep looking back and forth, so I'm just gonna mute my video again. So we expand Phagaris, this node, off the by picking it off the priority queue, and we get Sibiu, its successors, and Bucharest. Sibiu has a cost, this version of Sibiu, of 591, and Bucharest has a cost of 450 because its h of n value is 0, but its g of n path cost is 450. Okay, and so we look at this and we see that Pitesi is, even though Bucharest is a goal state, its value, its f of n, its evaluative measure, is not the lowest on the priority queue. It says that this particular path from Arad to Sibiu to Phagaris to Bucharest is not the best path to take because we have some path evaluative measure for Pitesi that is lower. Okay. So we pick Pitesi off the queue and we expand its successors. We get a new version of Bucharest. It appears multiply on the search queue, on the solution path. Bucharest, Craiova, and Rimniku Vileka. And this version of Bucharest that we encountered when we expanded Pitesi, it has an f of n value. G of n is 418, h of n is 0. Its value is 418. And one of the observations to make is that this is the lowest path estimate f of n, or evaluative measure f of n, that is currently on our priority queue. So it picks this version of Bucharest off of the priority queue, does the goal test, and returns back a solution because we've reached the goal state. Any questions about this? Does that make sense? No questions? Okay. I'll take that as a no. All right. So some properties of your heuristic really have an impact of the behavior and the quality of your solution path. And as we said before, your heuristic trades off optimality with efficiency. That's both in time and in space, namely the number of nodes you expand, time, and the memory that you use, the number of nodes that you place on your queues, be that the FIFO queue and or the encountered queue. And so The optimality of A star search is based on the design and the properties associated with your heuristic. And a key property is something called admissibility. An admissible heuristic is one that never overestimates the cost to your goal. As we saw with the road trip example from Kenmore Square to Newport, Oregon, when you compute that straight line Cartesian distance, as I think it was Alexander had answered, that roadways are not straight. And because roadways are not straight, any Cartesian distance that you compute, it's going to be the straight line distance. In some cases, it's going to be much shorter than the distance accumulated by looking at the roadway segments. In other cases, in other cases, it's going to be closer to, and in some cases, it's going to be shorter. And so what this overestimate means is, and we'll formalize that in a few slides, that it will never be greater than the actual distance you would compute by accumulating the individual step costs for traversing from one node to its successors along the way. And so because of this, our H of n, our path cost estimate, is going to be optimistic. It's going to say your goal is closer than it really is in truth. But that still has good properties that ensures that your A star search, your best first search based on this F of n equals G of n plus H of n, is still ensured that you're going to return an optimal solution. Okay. And so admissibility of your heuristic means that your F of n is going to return optimal solutions. Okay. And so in this diagram here, we have our G of n, our incremental path cost, and then we have our H of n, and I tried to kind of depict it as being a straight line. And if you were to kind of measure the length of this wiggly line, the length of the straight line H of n would be shorter than this wiggly line to get to your goal. Any questions? Oh, all right. And so admissibility means that your solution in A star search is going to be optimal cost. And in the book, they have a proof by contradiction for demonstrating that. And with this, let's imagine, as marked here, and in this diagram, these brackets here are, so you can think of them as these measurement instruments that measure distance. And on the right-hand side, let's imagine your optimal path has a cost that we're going to call C star, right? Let's also imagine that you run A star search, this greedy best first search using F of n equals H of n plus G of n. It has a path cost of C. And for the sake of this argument, let's imagine that C is greater than C star. Okay. Now, given the action of greedy best first search using this F of n equals G of n plus H of n, we said that it gives you the optimal cost path. But let's just assume that it returned a C cost, which is greater than this ground truth optimal path cost of C star. Okay. So if that's the case, that means along the solution path or along the path uncovered by A star, going from S to some intermediate node N, on through some set of nodes in our successors that we encounter to the goal G, there's going to be some node that has been unexpanded. There is going to be some node, there exists a node N that is on the optimal path that has been unexpanded. And the reason why we say it's unexpanded, because if the optimal cost path C star is less than what's returned by A star, by the action of A star, greedy best first search variant, that it means that this N on the optimal path was not expanded. Okay. Does that make sense? Any questions? No, I'm going to take that as a no. I'm watching the chat. All right. So let's imagine we have a G star And G star is that portion of the cost optimal path that goes from our start state S to that intermediate node N. And let's imagine we have an H star N, which is an estimate on the cost optimal path of that distance between that intermediate node N and our goal G. Okay. So we start out and imagine our f of n is greater as we expand than the C star, our optimal cost path. Otherwise, if it's n would have been expanded. So what I mean by that, and this is in the book, that it has to be greater than our optimal cost path because n would have been expanded otherwise, right? N is unexpanded, but because it's greater, if it has to be greater than our optimal, but certainly n would have been expanded just by the action of A star being a greedy best first search using a priority queue. So that means our definition of this f of n, we started out, is f of n is g of n plus h of n. Okay. Now, if n is on the optimal cost path, that means our definition of f of n, that g component has to be g star of n, because n, by action of greedy best first search, if it is on the optimal path, then it would have been selected off the priority queue along the way as you expand the frontier starting from S. Okay. Now, because this heuristic is admissible by definition of A star search, because it was given that you're running A star search, well, as an admissible heuristic, that means this H of n component is going to be of the form of what we see here. It's going to be at most or less than equal to H star n. Now, because of admissibility, we can replace this H of n with H star n, because again, greedy best first search selects the smallest evaluative measure, f of n. So we replace this H of n with H star n because of this admissibility principle. And we said A star uses admissible heuristics. And this expression, g star of n plus h of n, if we replace h of n with h star of n, then we use an inequality because this value of f of n is going to get smaller because h of n is less than equal to h star of n. Now, this being the case, okay, by definition, we said we arrive upon this path optimal cost, this optimal cost path, I should say, by using g star n and h star n. But if that's the case, that means this f of n, we say less than equal to g star n plus h star n. That would mean this f of n, this form, has to produce a path cost for the solution, which is the best cost path, which is less than equal to C star. But then we started at the outset a greater than C star. So by contradiction, we demonstrate that it has to be the optimal path cost. Does that make sense? Any questions? So we start out with a premise. We make legal transformations based on this premise, and we arrive upon our contradiction to complete our proof. Okay. No questions? No? All right. So another important property, aside from admissibility, is something called consistency. And consistency has to do with something called the triangle inequality. And I'm going to get my mouse here as my sketch pad. And I'm going to take this diagram and I'm going to draw a slightly different version of it, going from n to n prime. So n prime is the successor of n. And we're going to have our path cost estimate to get to the goal state from n prime. And then I'm going to draw sort of right next to it that path cost estimate directly from node n. So I'm going to decorate this with h of n. And I'm going to decorate this edge with h of n prime. Let me make that look like an h. And so the triangle inequality gets its name because if you draw a triangle, you have your straight line distance here, and you have a distance that you can achieve by traversing this edge and that edge. And what it says is that if we measure the distance here, that distance is at most the sum of these two distances. It's almost like talking about the Pythagorean theorem, but it's not the Pythagorean theorem. And so in this diagram, we start out and we have an arbitrary node n, and we have a path cost estimate to get from node n to the goal. And we have an alternative route to get from node n to the goal through expanding its successor to get to that edge, that one step between n and its successor n prime, and adding to that the path cost estimate from n prime to the goal. And so what consistency says is that this h of n is at most or less than equal to the step cost for that single transition from n to n prime, its successor, plus the path cost estimate to get from n prime, its successor, to the goal state. And in this, it's the successor of n prime that's reached through a single action. And that action is associated with a step cost that you get from your environment dynamics. And so this idea of consistency or triangle inequality, it's a much stronger property than just admissibility. And it says the first time you reach n, right, that's when you encounter this node n, it's on an optimal path. If it's on an optimal path, you're going to find that optimal path using your path cost estimate. Does that make sense? Any questions? Okay, thank you. And so a consistent heuristic satisfies a triangle inequality, by definition is admissible, but the reverse is not true. An admissible heuristic is not always consistent, right? And so the family of admissible heuristics is bigger than the family of consistent heuristics. If you were to draw a Venn diagram, you'd have the admissible. I'm drawing with my mouse, so I'm going to abbreviate here. And then inside of it is consistent. So consistent heuristics are by definition admissible, but the converse is not true. Okay. Any questions? No? All right. And so with this, it means a state is not added to the frontier multiple times. In essence, a consistent heuristic is going to want to prefer to drive down the search tree and not repeat states. The first time it encounters it, it's going to find it, the version that is on the minimum cost path. If you have and for that reason, I just forgot what I was going to say. A state is not added to the frontier multiple times, like we saw in the previous example for the Romania trip. And that means that you're not going to have to perform updates on the reach data structure because you encountered it a second time and you're now updating its weights, its evaluative measure, to make sure that you're getting min cost paths. You can have an inconsistent heuristic. With an inconsistent heuristic, which is what we saw in that Romania example for A-star search, you can encounter multiple paths through an arbitrary node as you're expanding your frontier. And we saw that. We saw Bucharest appear twice. We saw Sibiu appear twice. And so what the cost that you see is time and space. you're going to get a savings in time and space because you're encountering nodes only one time as you expand the frontier, because you're generating those nodes that are on these the optimal solution path. Okay. Any questions? Excuse me. All right. And so one of the things you could do with A-star search is you could only allow, if you're inconsistent in your heuristic, you could force the idea of allowing only single appearances on the frontier. Okay, if you find a better cost path through an intermediate node you encounter as you expand the frontier, you're going to have to change some things, right? And the things you're going to have to change is the ability to rewire the solution path to represent the new solution path from that new version of the intermediate node proceeding forward to the goal. And in order to do that, the burden, while you can get a time savings and you can get a memory savings, the burden is on the complexity of your implementation. You're going to have a doubly linked list that both identifies the parent references for that node as well as the child references. And so if you encounter, for example, Sibiu twice, some arbitrary node n, and the second time you encounter it, its evaluative measure is an improvement on the other time you've encountered it, the first time, because it's not selected first when it's bigger, then you're going to have to go ahead and fix up that first version to have child pointers to the goal that are reflected in the better version of n that you encountered the second time. Any questions? So it's not horrible to do that implementation, but you're adding complexity to your implementation. But the good news is the savings in memory and in time is going to be paid for that complexity in your implementation. All right. So imagine if you have some heuristic and that heuristic is inconsistent. And let's imagine further that it's admissible for only a single cost optimal path. For all of the other paths, it's not admissible. And so imagine then for each of the nodes on your cost optimal path, it's going to find that solution, okay? But it doesn't really matter for all of the off optimal cost paths. I can't say that very fast because it's going to effectively prune those things that you consider, okay? So let's imagine then you have an optimal cost for your optimal cost solution path, and that cost is C star. And let's imagine you have a second best path. It's larger than C star, and we're going to call that C2. And if we have those two paths, one of the things we can do to trade off between this inadmissible heuristic that's only good for a single path, we can trade off and our overestimate that this heuristic is going to have when you perform search is going to be bounded by the difference between the second best path and this optimal path. And so even if your heuristic, what this is saying, even if your heuristic is not amazing everywhere, you can still get decent performance out of it as long as it's optimal somewhere, and that somewhere being a single path through your search tree. Does that make sense? Any questions? And I'm looking at my clock to make sure I'm on time. All right. And so that means even with a less good heuristic, you can get bounds on your optimal cost path, which isn't bad. So if you fudge it with a heuristic that's not the best, you can still do well in clever ways by looking at your second best cost path versus your first best cost path. Does that make sense? All right. So here's an example visualization, and this is in the book, and it talks about thinking about how your search proceeds as you use these evaluative measures of the sort that you would have with A-star, this combination of your G cost, your solution path cost to the intermediate node, plus your estimate H of n. And they think of it as kind of like an amoeba, a blob, or an expanding band, if you will, of search. And this band monotonically increases in the amount of cost relative to the nodes that might fall within that band of cost. And so in this example, if we look at the second expansion of this band, at most 400 in this example, it evaluates all of the nodes and counters all of the nodes whose performance measure f of n in the priority queue is less than equal to 400. And then once it exhausts all of those nodes that fall within that performance band, it increases the band and then continues its search for nodes whose f of n value, evaluative measure, falls within that next version of the band. If we look at uniform cost search, instead of this eccentric ellipse blob that kind of expands downward, we can think of it as concentric circles that project outwards equally in all directions. And so this idea of contour lines, these expanding concentric bands, because in A-star search, our successors have a step cost that's non-negative, these bands are either going to stay the same or they're going to increase. They're going to be monotonic over time. So that means they will get bigger or stay the same. But if this stays the same, we're going to eventually exhaust all the nodes at some point that fall within that band until we encounter a non-zero step cost, and then the band's going to expand, and we're going to continue to examine nodes, pulling them off the frontier queue that are in the new band. And so the question then is, are path costs monotonic? Which is an important consideration that we can take advantage of to use this performance measure, more specifically the heuristic, to effectively prune the nodes that we pursue when we're expanding the frontier. Okay, and so we start out with an evaluative measure, G of n plus H of n, which is the evaluative measure that we have for some arbitrary node n. And we look at the step cost. The step cost is a value that's non-negative that gives you the cost of going from node n to its successor, n prime, through one of the admissible actions available to that node n. So given our step costs, what we're enterprising to do is prove that our G of n is monotonic. Okay, so we start out with n, and we take a transition. And we take this transition to n's successor that we'll call arbitrarily n prime. In this case now, our evaluative measure changes. Our evaluative measure in state n is G of n, the path cost, plus H of n, the estimate to the goal. When we take that step, our cost changes to G of n plus the goal, the cost for the path estimate to the goal of n prime, our successor, plus the unit step cost. So our measure goes from G of n plus H of n to G of n plus the step cost plus H of n prime. Okay. So we take this expression, and we know that for each of the expressions, what we started with and what we ended with for the evaluative measure once we reached n prime by expanding the frontier from n, we get H of n on one side, and we get our step cost plus H of n prime in the other expression. And the path cost is monotonic if H of n is at most our step cost plus h of n prime? Well, the path cost is monotonic if it's consistent. And this condition that we have is exactly consistency that we had from before, the triangle inequality. And so if our h of n is consistent, satisfies the triangle inequality, then our path cost is going to be monotonic, meaning that as we expand the contours of our search frontier, that radius, that contour, and namely the and therefore the nodes that we explore are going to be within that band, and that band is going to be monotonically increasing. And what that means is that we're going to advance stepwise by stepwise by stepwise, ultimately arriving upon the goal. And so our path cost is monotonic can be demonstrated by proving that our heuristic satisfies the triangle inequality, it's consistent, and we know that consistent heuristics are also admissible heuristics. They underestimate the distance to the goal. Does that make sense? Any questions? You still there? All right, thank
still
you.
here.
Okay. All right. So if you're given an optimal solution cost, then what does A star do? Each node reached from the start state that is within this optimal cost are termed surely expanded. They will be reached. Once your cost afforded by your performance measure is exactly equal to the optimal path cost, you could have the goal node at that optimal path cost, but you could have a number of other nodes at that optimal path cost. But you're going to expand those nodes on the so-called goal contour. And the nodes on the goal contour are different from those nodes that are surely expanded, because surely expanded refers to those nodes within that search contour that's just before or just smaller than that optimal cost C star. And so nodes that are outside of the goal contour, they're not expanded. And so effectively, what this idea is expressing is that we're only going to search nodes that we need to get you to that optimal path cost. And we're going to ignore other nodes that are outside of that optimal path cost. So this means it's optimally efficient if we have a monotonic heuristic. Does that make sense? All right. And so why did I say this? Because this monotonicity affords you savings in time and in space. And so here we have an expansion of the search tree from A star search, and each node is decorated with the evaluative measure, which consists of the path cost G of n and the goal estimate H of n. And so here we see, to get my mouse working, that these subtrees that I've identified with the dotted lines, those subtrees are not even considered when I do my expansion. And effectively, those subtrees, if I were to list out their successors, would represent a large number of solution paths that I could possibly explore when I'm searching for the goal. Now, I'm only displaying the top of these paths, but when we look at the number of nodes, and if you were to compute some notion of the upper bound on the number of successors any node has in the expansion, you have a lot of solution paths that you could consider if you were doing an uninformed search. And so in effect, what this visualization is showing you is that by going with the quote unquote right heuristic, you're to a very large degree pruning from consideration a large number of possible paths through this search tree that you could consider. Now, those paths that it does consider, because of this preference on the Q for those smaller values. And because of those characteristics, admissibility, consistency, there are a lot of solution paths that don't even get considered. Mind you, yes, they still get placed as they're encountered onto the encountered queue. But when we actually do our expansion, we're only visiting a much smaller number of our nodes along and considering fewer paths than we otherwise would have. And so in essence, we're pruning search nodes. And the search nodes that we're pruning or eliminating from consideration or not considering are those that are not necessary towards ultimately building optimal solution paths. And so in essence, we see that Timisoara in this example had an evaluative measure of 477 and Zerend of 449. These were both successors of that initial expansion of our start state Arad, our start node Arad. But we didn't even consider these successors nor any other paths in trees rooted in these successors of Arad. So we got an enormous savings, both in time as well as in space, we would have needed to store these on our data structures, both the encountered queue and the FIFO queue. Does that make sense? And the priority queue, I should say. All right. And so we get a savings, and these savings are in contrast to uniform cost search, whose frontier is a contour that's a concentric circle that expands equally in all directions, and breadth first search, which placed all of the successors on the tree, and we saw that it had a complexity of big O of B to the D, where B was the branching factor and D was the depth. And so this heuristic and searches that make use of heuristics afford us a tremendous savings in time and in space. Okay. And so I'm going to end, we have, well, one more minute. I'm going to end with this. So it's important to prune. And pruning is how you get searches and solution finding to work in practical sense with complex environments, because you can't possibly do an exhaustive search. You need information about the environment encoded with your path cost estimate, your heuristic. But then based on the properties of this heuristic, you can get desirable properties that it won't even consider a solution path if the nodes expanded on that frontier or the nodes explored in that contour, search contour, are not helpful in terms of being nodes along an optimal solution. Okay, I don't know what I just did. All right, there we go. So that's about time. We have 30 seconds. We'll end there, and we'll pick back up on Thursday with some code walkthrough, because we're a little bit ahead with this material. But one of the questions on the project number 2 deals with A-star search. And so again, you're going to need to examine information about your state space. Like we started at the beginning with the road trip, you're going to need to know things about the positions of things. And we see that straight line distance in that example is a perfectly fine heuristic. But in your consideration for your heuristic, you have to make sure it's an underestimate and not an overestimate. With inadmissible heuristics, you can still afford savings, but admissible and consistent heuristics give you this immense pruning. Okay, so I'm going to stop the share. We'll end there. Oops, we'll end there. Let me bring down the slides and let me stop the recording, and we'll pick back up on Thursday. Stay safe, stay warm, and don't forget to go out and have some fun in the snow. That's really important for getting through periods like this. So I'll see you all on Thursday. Take care. All right.
Thank you.
Thank you.
You're welcome. Take care.